Yes, class. Good evening. Am I audible to all of you?
Yes.
Okay. So we had completed till intrinsic semiconductors. This part was completed. We had to start from extrinsic semiconductors. So intrinsic semiconductors were the pure semiconductors, which had no impurity present. Whatever atoms of silicon were present, so exact atoms of silicon will be present here also. Fine. Now, limitations we did, we have to start with extrinsic. See, class, extrinsic semiconductors means now you will be having some amount of impurity. Certain amount of impurity will now be present. So impure semiconductors that have desired impurity atoms in the crystal known as dopants. See, meaning is what? You have a proper crystal lattice with you. The way we had silicon crystal lattice with us, so you have a proper crystal lattice with you. If I put some atoms and I bring certain atoms into this crystal, fine. This was a pure crystal. Now I have added certain atoms into this crystal. Now what will happen? Now this crystal is no more pure. It becomes impure. Let's say silicon crystal was present. Everywhere you had silicon. In between you have taken phosphorus. So now phosphorus atom is not a part of the pure crystal lattice. Now the crystal lattice along with phosphorus is becoming an impure crystal. So the atoms that are added into this crystal to make it impure, you call this as dopants. And this entire process, this is known as doping. So process is known as doping. The atoms that are added, these are known as dopants. Now, depending upon the type of dopants, whatever type of dopants have been added, there are basically two types of dopants: pentavalent dopants and trivalent dopants. So you must be knowing all those periodic tables families: phosphorus family, boron family. So phosphorus family has 5 electrons in its valence shell. So all the atoms that have 5 electrons in their valence shells, those are known as pentavalent dopants. The entire phosphorus family that is present in your periodic table, you must have learnt of which. Like, how do you write phosphorus? You write phosphorus with 5 valencies, like this only. And those are having 3 electrons. They are known as trivalent dopants, like the entire boron family. Whole boron, indium, aluminium, gallium, thallium, and all these. How do you write aluminium? Al3 plus. So this makes it trivalent dopant. Now, depending upon the dopant, see, again class repeating, 5 electrons for pentavalent, 3 electrons for trivalent. Fine? Class, note down this. Now, depending on this, we'll be having two types, N type and P type, that has to be discussed, that is left to be discussed. Note it down, note the space, then we'll start with N type first. See class. Now, depending upon the type of dopants, whether it is pentavalent dopants or you're using trivalent dopants. So, depending on the dopants you're using, you will be having two types of semiconductors: N-type semiconductors and P-type semiconductors. So, if you use pentavalent dopants having 5 electrons, then you get the type of semiconductor which is known as N-type. And for P-type, you have trivalent dopants. So see, suppose let's say a proper crystal lattice is there. This is an entire crystal lattice that is present. So silicon-silicon bondings are there, and I have already told you that the straight, instead of drawing the straight bond, I am drawing like this. Like this. Fine. So now silicon has 4 electrons. So for silicon, all the 4 electrons will be present. For phosphorus, what will happen? 5 electrons will be there. 1 electron will become extra because it has 5 electrons in the valence shell. So all these will interact and make covalent bond, but 1 electron will be left extra. Understood? Here 1 electron, this will be left extra. Now see, what will happen? This extra electron, this is a weakly bonded electron. This is weakly bounded electron. So if you get a sufficient thermal energy, some energy around 0.045 electron volt. If you get energy around 0.045 electron volt, this much amount of energy you're getting, that is the thermal energy. Thermal energy. Then what will happen? This electron was already weakly bounded because it was present in the outermost part and it was not even sharing and making a covalent bond. So this is weakly bonded. Now what will happen? As soon as this thermal energy is met to the electron, this weakly bounded electron becomes free electron. So here in N type of conductors, majority charge carriers that will be present will be electrons. Means number of electrons will be far, far greater than number of holes. This will be the condition for N type. Understood? A majority charge carriers are electrons. You have to remember this because after this we'll be doing PN junction. And in PN junction, this topic is used a lot. Majority charge carriers, minority charge carriers. So for majority charge carriers, you have electrons in the N type. And why do you have electrons in the N type? Because your silicon, germanium, all these are mainly the crystal lattices that are present. So all the dopants that are present, those have extra electrons. And because of that extra electron that is present, you obtain more of negative charges. More negative charges are there, more electrons are present as compared to holes. Holes and electrons we had discussed in the last class. Fine. Now, even if you draw the energy gap for this, see, energy band gap also if you draw. Okay, so impurities are added in parts per million. Impurities are added in parts per million, small 10 to the power minus 6. Now, electron are generated by two mechanisms. Yes, one more thing, class. See, these atoms, these donor atoms are doing what? They are actually donating some extra electrons to the lattice, crystal lattice. Earlier, this was neutral. All the negative charges was equal to the positive charges. So now what will happen? Since you have extra amount of electrons, it is making it negative. Some amount of extra electron is present. So that is donated by the phosphorus atom that has come. Earlier, this electron was not present. Earlier, it was all neutral. So we call these dopants, pentavalent dopants in N-type semiconductors as donor atoms. These are donor atoms. So either directly donor atom can give the electrons or the thermal energy can meet the necessary function that is required. So electrons are generated by two mechanisms. So through donor atom, means no concept of hole, directly the atom is donating, and thermally generated hole. Thermally generated hole means through thermal energy, and the energy amount also I have told you. That amount you don't need to relearn, you have to learn this learn it because this is for silicon and germanium. Any data that you have to remember in this lesson is for silicon and germanium. And number density of electrons is much greater than that of holes. See, even if you draw the energy band gap, do you all remember? We did in the last class. Conduction band was there. What was another band that was present? One more band was there, no? What was that band? Conduction band was there. Apart from conduction band, what was the band that was below?
Valence band.
Valence band. So this is valence band. Krishna, have you just joined? Or you had joined the class?
No, ma'am, I joined earlier itself.
Okay. So valence band has electrons. So now see class, if you look here, the energy band gap that is present, if you apply the energy band gap theory, see here, over here, this was the lowest energy level of the conduction band, whereas this was the highest energy level of the valence band. So the gap that you obtained was known as energy gap. This part we did. See, for the n-type conductor, no, the energy band that will be lying at this place, here, somewhere here, this will be around 0.045 electron volt. And this is actually for silicon. For germanium, if you draw this and write this energy gap that you're obtaining, this energy gap. For silicon, it is 0.01 electron volt. This is for germanium. So these are the energy level of donor atoms. Energy level of donor atoms. Fine. And what is this energy? This energy is ionization energy only. Energy that is required to completely remove an electron from the atom. So this is ionization energy to completely remove the electron. If this is the nucleus, from the to completely remove this electron out of the atom, that energy. So for silicon and germanium, it is specifically mentioned. The rest of it has been discussed. So again, I'll just repeat, in p-type semiconductors, what will happen? In p-type, you have greater amount of electrons present. Electrons are present more than the holes because the atoms are donor atoms. These donate extra electrons. Opposite case will be in case of p-type. Now you can predict for p-type, whatever things you have studied for n-type, exactly opposite will be there for p-type. See, in case of n-type, in n-type we use pentavalent dopants. So in p-type we'll be using trivalent dopants. Like in the silicon crystal lattice, now let us put in between aluminium. Like this, if we put aluminium, see, so now what will happen? Silicon will be having its 4 electrons, but aluminium will be having 3. Now there is a need of 1 more electron. So what will happen? This electron that is present, no, within this silicon-silicon bond, this will move, and here it will allow it to complete an octet. Now, what did we discuss in the last class? If an electron moves, what is created over that place?
Energy.
Energy. Electrons move. Deficiency of electrons.
Holes.
Holes. Good, Fatma. Holes. So if electron moves from here, a hole will be created here. And now the electrons are now, no more electrons are present which are available for conduction because the bonds have been made, octet has been completed. But now if you look, this hole is available for conduction to occur. Now this is just one single piece, no, that I have shown you. When you will see the whole complete atom, so many silicons will be present in between, aluminium atoms will be present in between. So each aluminium atom will be contributing for a whole. So what will happen here? Here you will not be having any electron excess in excess. All the electrons will be bounded. What will happen? You will be having more amount of holes, because all this, what happened in this case, the way to complete the octet, this electron jumped. Same way, wherever aluminium atoms are present, the silicon atoms will break their bond, electrons will join and make the octet complete, and there will the vacancy. As soon as the electron leave that vacancy, we call it as hole. Why is there a need? Because initially, when no bond was made, you do not call that as whole. You call the entity as whole when electron has specifically left that place. Otherwise, this like this, here you do not have any electron, so you will not call this whole. If this electron leaves this place, then you call it as whole. So that's why we are getting more amount of holes. So each atom of aluminium contributes for holes. So as a result, now number of holes will be greater than number of electrons. So if you are asked what are the majority charge carriers in p-type, that will be holes. Minority charge carriers in p-type, electrons. And unlike this, you will be having majority charge carriers as electrons in n-type and minority charge carriers as hole in n-type. So again, how these electrons are generated, these electrons are again produced by two mechanisms. One more thing, class. Aluminium did what? Aluminium atom didn't give any electron of its own. Rather, it accepted one electron. So here you will be this aluminium. This will be since it accepted the electron, this is known as acceptor atom. And the atom that was phosphorus. So phosphorus was donor atom because it gave an electron. Here this was accepting electron, so this is known as acceptor atom. So again, this is produced by two mechanisms. Acceptor atom can directly accept it, or sufficient thermal energy can be required to meet it. And here if you draw the band gap, band theory, conduction band is present, valence band is present, this is energy for conduction band, highest energy level for valence band. This gap is known as energy gap. Now this will be lying near the valence band. This is the energy level of the acceptor ions. So C class, for n-type of semiconductors, the majority charge carriers are electrons because they are greater than holes, and holes are the minority. Whereas in p-type semiconductors, majority charge carriers are hole and electrons are minority charge carriers in p-type, because we'll be doing after this p-n junction, and there this concept is required. Majority, this is the majority here. Holes are the minority in n-type, whereas holes are the majority in p-type, and in minority are the electrons that are present. Number density of holes is NH, number density of electrons is Ne, and number density, this is holes and electrons are used for extrinsic semiconductors. We did intrinsic semiconductors also. So number density of the total intrinsic semiconductor that is present. There is one relationship between all three. That is, see here, Ne is number density of electron, this is number density of hole, and number density for intrinsic semiconductors. Ni square is equal to Ne multiplied by NH. So formula-based questions are not usually from this. We'll see if question you have questions basically from electrostatic, number of electrons and all that gets related to what we have already studied in electrostatics. Number of electrons, all those questions that are present in your in-text questions and back exercises of NCRT. Otherwise, this was all about p-type, n-type, extrinsic and intrinsic semiconductors, basically the types of semiconductors. Now we have to complete PN junction. Do one thing, note down all this part, all these points. Any difficulty you have, any doubts you have, let me know. Then we'll start with PN junction. No, Hamza, numericals are very few from this lesson. Earlier numericals were there from transistor portion. Entire circuits were there. You don't have you have numericals, but that will be very much similar to current electricity. After PN junction, I'll tell you. Yes, class. Now coming to PN junction. See, PN junction means you have a single crystal, and within this crystal only you have doped one side with pentavalent atoms and other side with trivalent atom. So the side receiving trivalent atom will be P type, and the side that will be have receiving the pentavalent atoms will be N type. So P type and N type semiconductors on the same side. Just a second. Yes, class. So one side you have P type, on the other side you have N type semiconductor. So it's not like you have taken P type and N type and you have joined it by some means. No. P type and N type have been constructed only in a single crystal. So PN junction is what? It is a single crystal. So see, it's a single crystal doped with pentavalent impurity in half portion with a trivalent impurity in another half portion. So that half of its act as P type and other half acts as N type. Now see class, what will happen? Two important processes will be involved here. One process is known as diffusion, other process is known as drift. So first process is diffusion, another process is drift. See here what will happen. When PN junction is formed, P side of the junction has what type of charge carriers in majority? I have told you this. Anyone who can answer? P type majority charge carriers in P type.
Plus.
Holes, yes. Holes. Plus are the holes. So holes will be in majority in P type, whereas there will be very few in N type. They will be present, but very few. We have seen majority and minority. In N type, electrons will be more. Here, the amount of electrons that will be present, this will be a lot. Whereas you will find very few electrons that are present in P type because those are the minority charge carriers over there. Now see class, what happens? This leads to development of what? Concentration gradient. When a PN junction is formed, P side of the junction has a higher concentration of holes while the N side has a higher concentration of electrons. So due to the concentration gradient at this junction, holes begin to diffuse from P side to N side. P side to N side, all these holes are moving. Whereas electrons begin to move from N side to the P side because of the concentration gradient that is developed. Now, as holes diffuse from P to N side, if holes are moving, they leave behind negative impurities. Negative ions will be left, or every hole that will be leaving, it will develop a negative ion, right? And similarly, when the electron will be leaving, when electron will be diffusing from N to P side, it will leave behind a positive donor atom. It will donate a positive donor atom, all the electrons. So ultimately, a negative accumulation will be observed near the P junction and positive layered accumulation will be observed near the N type. Why? Because negative electrons are formed because of the holes leaving. And since electrons are leaving, positive is formed at the junction. This phenomena that had occurred where the majority charge carriers left their place, electrons from N type and holes from P type, this process is known as diffusion, the first process that I was mentioning. This process is known as diffusion. Fine? First process is diffusion. Now see, after when this occurs, though a negative and positive charges have been set up. This sets up an electric field further from N to P side in the opposite direction. From N to P side, electric field is developed exactly in the opposite direction. So any hole near the junction is pushed towards the N side. Any hole that is formed, it will be pushed towards the N side. Now what will happen? A potential will also be present. And here, this region that you see, it will keep on expanding. This region that you observe, this is known as depletion layer. Depletion region, you can say depletion layer, you can say depletion region or depletion layer. Now, once this electric field is set up, here, let's say this electric field has been set up. Now, what will happen? Once the electric field is set up, another conduction of electron will occur. It means now it will be in opposite direction. All the positive charges, because see, this is positive, this is negative. It will be attracting all the positive ions towards itself. And this positive terminal, this will be attracting all the negative electrons. So it means electrons from P type will move and holes from N type will move. That is movement of minority charge carriers. So that phenomena where minority charge carriers move, it is known as drift. So first process was diffusion, second process was drift. So P type, on this side you have, N type you have. Electric field got developed. Because of electric field, you will have a potential also. That potential, we call it as barrier potential. So this potential is known as barrier potential. And this is actually a fictitious battery. You do not actually put a battery. This battery I'm just putting to show you, to make you understand. Fine. It's just that it is making you to understand that barrier potential has been created. This is just a battery that is actually not present in the region. This is just I'm making it so that you understand how the minority charge carriers are moving. Also, class, when in diffusion, when the electrons were moving, that time you can call the current that is flowing as diffusion current. All right. So diffusion is flow of majority charge carriers across the junction from P to N and electrons from N to P. And barrier potential is what? Accumulation of charges in P and N region that sets up a potential difference known as barrier potential. This potential sets up electric field across the junction which opposes further movement of majority charge carriers. And since it opposes, because of this opposition, you get the flow of minority charge carriers. Earlier, it was majority charge carriers. Now, minority charge carriers are moving, which is known as drift. C class, again, I'm repeating in N type. Majority charge carriers are electrons and the minority charge carriers are the holes. Whereas in P type, majority charge carriers are holes and the minority charge carriers are electrons. Note down this, then we'll see further PN junction diodes. See class, how to depict this? These are basically diodes. If you put the metallic contacts apart on the sides of it, that makes it a complete diode. So diodes we'll be using here. You will be having diodes. But see class, now one thing, it's not possible to draw this entire setup every time, obviously, no? So for P type, we draw this triangle. For N type, we draw a straight line, right? Now what will happen? If you will draw PN junction, P type, N type. So can you see in your circuits and everything, you can use this simply. All these questions, as I was telling to Josefa, I think, yes, Josefa was telling that you will be getting questions similar to current electricity. So here nothing new will be present. Whatever portion you have in current electricity, that part will come. I'll show you the question. Let us first complete biasing. And if I want to write N first, NP, then I'll write it like this, NP junction. Clear? Now see, if the P type is connected to this diode, diodes are connected in our circuits for industrial purposes and many purposes. So if in the circuit, P type is connected to the positive terminal of the battery, then we say this is forward biasing, and N type is connected to the negative terminal of the battery. Very few observations you have to make, but whatever observations I have written it on the screen, those please remember. Apart from this, even if you do not remember anything, that will be fine, but these are very important. C class. Forward biasing in forward biasing, there will be flow of majority charge carriers across the junction. Diffusion process will occur. Majority charge carriers will cross the junction. Understood? It means holes from the P type, electrons from the N type. Please class, the basis of this chapter is just this part only. The crux of the whole lesson, PN junction and everything is just majority, minority, diffusion, drift and everything. Pentavalent dopant for NNP type, and after NNP type, you have majority and minority charge carriers. Apart from this, nothing is difficult in this lesson. It's very easy to score in semiconductors. The portions that were difficult earlier, that has already been deleted. Transistors are not a part of your syllabus now. So many filter circuits and everything has been deleted. Special purpose diodes are also not available now. So you just have to do the simple PN junction diode. Zener diode, you don't have to do. Photocells, solar cells, photodiodes, all these you do not have to do. So just focus on this part only. So I was saying majority charge carriers will flow in forward biasing. So barrier potential, what will happen? This is, let's say the barrier potential will be across the junction, and there will be a potential of the battery also. Battery will be having its potential also. So net potential will be difference between this. That means it will lead to reduction in the potential. Fine. What will happen to width of depletion region C? Let's say this was depletion region. Let's say this was depletion region. Fine. Now what will happen? When the electrons will be leaving, because majority charge carriers are moving, so it will form a positive charge here, and from here you have a negative charge. So once biasing is done, class C, positive will attract the positive part, that will lead to negative. So one negative will be recombining with the positive, then negative recombining with positive, then negative recombining with positive. Positive, negative, when they interact, it leads to neutralization. So here also neutralization will occur. So what happened to the width of this depletion region? Did it increase or decrease, class? Decreased. So width of depletion region, this decreases. Fine. And here what happens? Resistance of the depletion region is also very less. The depletion region's resistance is also very less. So if resistance is less, current will be more. So that's why we measure this in milliamperes. We measure this in forward biasing in milliamperes. Now class. So all the points I think I've discussed: flow of majority charge carriers, barrier potential decreasing, width is also decreasing, resistance is decreasing. In reverse biasing, C class, the reverse biasing will just take 2 to 3 minutes. See, It will be exactly the opposite. When p-type is connected to the negative terminal and n-type is connected to the positive terminal of the battery, that will lead to reverse biasing. You call this type of biasing, this connection of the diodes in the entire circuit. This is known as bias. Now minority charge carriers will flow. So now what will happen? Plus this negative terminal of the battery will attract all the electrons from the opposite side. That will lead to more amount of holes. And similarly, from the positive side, that will attract all the negative ions, all the positive, that is the holes, it will attract holes. So here you will be having more of negative ions. What is happening to the depletion region now?
Increasing.
Increasing. So depletion region increasing in case of what? Reverse biasing. Now barrier potential, this becomes the sum of both. Basically the net potential increases. One potential is from the battery, one potential is from the PN junction. So both increase, they add up and it increases. Now resistance is more, so current will be less. So that was milliamperes. Here you will be measuring current in microamperes. This is a very good thing to identify whether your circuit is in reverse biasing or forward biasing, even if you are not able to identify it by the terminals and rest of the things. See in your circuit whether microammeter or milliammeter is connected. If it is milliammeter, it will be forward biasing. Microammeter, reverse biasing. Fine? So in reverse biasing, you have flow of minority charge carriers across the junction, barrier potential increases, width of depletion region increases, resistance also increases. This is all about reverse biasing. When one very good type of questions that come are from, now the questions that will come from the numerical type, these will be from this portion only. Before identification or note down this part, read it also. Any doubts you have, let me know. Because from here only you will be able to identify this. Note it down, then we'll do those type of questions where you have to identify. This is all about the theory of PN junction. Very small portions are there in your semiconductors class.
Ma'am, could you show the definition of drift?
Yes, drift, no?
Done, ma'am.
C class, for identification of whether your circuit is connected in reverse bias, forward bias, if you are not able to observe it by just looking at the terminals of the battery, then you have to look at by the potential. See here, the one that is connected to the, if P type is connected to the higher potential and N type is connected to the lower potential, that means it is forward biased. Highest with P type, lowest with N type. If opposite is there, by chance you see that P type is connected with the lower potential one and N type is connected with the higher potential one, then it means that is reverse biasing. So by looking at the potential also you can, like, see the first question here. In the first question, P type is connected to 10 volts, N type is connected to 3 volts. P with higher, N with lower. Fine. So this is forward biasing. Look here in the second question. P is connected to 3 volts, N is connected to minus 3 volts. Again, minus 3 plus 3 is greater. So P is connected with greater one, N is connected with lower one. So forward biasing. Look in the third one. Can you answer forward or reverse biasing? Third one.
Reverse biasing.
Reverse biasing. P is connected to 5, N is connected to 10. So N is connected to higher one and P is connected to lower one. So that is not, for the reverse biasing, not for the forward one. So this is reverse biasing. Yes, class, answer me in the chat box for fourth one. All of you answer. Reverse or forward? Or just simply write R or F. No need to write the complete, just write R or F. Correct. It will be C. Minus 10 and minus 3. So minus 3 is greater than minus 10 and N is connected to the greater one. So Fatima, Krishna and Hanifa, correct. This is reverse biasing. Class, remember the symbol for earthing we had studied when we were discussing electrostatics. This symbol was for potential 0. So see, if potential is 0 here, N is connected to 0 and P is connected to plus 5. So 5 or 0, 5 is greater, P is connected to greater one. So forward biasing. All of you answer for the sixth one now. Last part it is. Answer me in the chat box right now. Others also, Atif, Hamza, Zephyr is left for namaz, Hiba, Sara, Zain. Fatima, Hanifa, Atif. C, Atif and others. Hamza is also answered. Okay, Hamza, Krishna, Fatima, Hanifa, Atif. C class. This is potential 0. So 0 and minus 2. 0 is greater, no? So it would have been forward biasing if this was minus 2. This is reverse biasing. Rest of you are correct. 0 and minus 2. 0 is greater than minus 2. So N is connected to higher one. That is reversed. Reverse biasing. Like this, first you have to identify. By this you can identify or by just looking at the terminals. Now, one question I'll tell you how these diodes are used in your numericals. Just note down the space, then we'll discuss the question.
I'm in the sixth question. The minus 2 is connected to the earth, right?
No. Minus 2 is here. This is showing, no. This is showing here the potential is 0. But minus 2 is actually a part of circuit. We are not solving the circuits. That the concept that you are mentioning, no, Atif, that is for when you're solving the circuits. Right now, you're just checking whether it is reverse or bias. So for checking, just see the final terminals which are connected. Rest of the part that you will see in the circuit, which you're mentioning. Got it?
Yes, ma'am.
See, for the third one, no, this is 5 volts, this is 10 volts. We have to see if P type is connected to higher one and N to lower, that will be forward. If not, then reversed. See here, among 5 and 10, 10 volt is greater than 5 volt. And N is connected to higher one and P to lower one. So N to higher one, P to lower one, that is reversed. We wanted P to be connected with higher for forward. So that's why reversed biasing. Clear? The third one? Done.
Done, ma'am.
All right. See how the circuit questions come. Yes, for understanding the circuits question, no class. Just see. When identification you have studied, for forward biasing you have seen, and for reverse biasing you have seen. If you're able to identify that in your circuit, a diode is connected which is forward biased. So see, if it is forward biased, then your diode is replaced with a straight wire, which we call as short circuit. If you replace it with a wire, the rest of the circuit diode is vanished, a single wire is there. You know how to solve circuits. Circuits have been already studied. That's what I'm saying. In current electricity, whatever you have studied, same thing will be applied here. And if it is a reversed biasing, then it is open circuit. So if you see wherever you see reversed biased diodes, remove the diodes from your circuits. So that makes it open circuit. Let me show you a question. Look here. See the above one. This is first one. This is second one. Can you tell me first and second? Answer me in the chat column. First is forward bias. Second is forward. Second reversed. First what? Yes, class, answer in the chat column. Just write R and F, 1 R, 1 F, like this. Quickly answer all of you, otherwise I'll call out names and ask you all. Okay, only Hanifa is trying. Krishna, correct. Both the parts correct. Atif, correct. Hanifa, just check once again. Fatima, which one? First one?
Yes, teacher.
Say yes. Yes, others, Fatima, Atif, Krishna, Hanifa. Only 4 students have tried. Hamza, what about you? Hiba, Shara. See in the first one. Hanifa, listen. P is connected to positive terminal of the battery. So when P type is connected to positive terminal of the battery, that is forward biasing. So first one is forward biased and second one will be reversed biased. Any doubts in the identification, please let me know, class. Now what we have studied, first one will be replaced by a straight wire, while the second one will be replaced like this, open circuit. So how will I draw the proper circuit? 10 ohm will be connected. No need to draw this. This is reversed wires, open circuit. Leave the circuit. Battery and this 10 ohm. 10 volt. And so now you know equivalent resistance will be 10 plus 10. That will be 20 ohms. So even in complex circuits, if in addition to inductors, capacitors, resistors, you get a diode, diode's theory is not different. Like inductors had to be solved differently using EMI, laws of EMI. Capacitors have totally different formulas. Resistors have their self theories. For diodes, you do not have anything such like this. Replacing, you should remember which one. Do not get confused in the middle of paper whether in forward you had to write it or reverse you had to write it. Fine. So whatever you have studied in current electricity, exactly you will be solving the circuits. Parallel है तो parallel. Series, you're finding it in series, तो write down it in series. जो भी circuit है, as it is, write it for whatever you're getting. Forward to forward, reverse to reverse, replace it with a wire for forward, reverse के लिए तो हटाई. Simply remove the circuit. Remove the diode and rest whatever is left. Because in this branch, no current is flowing, so no need to draw this. Fine, like this, you have questions from this. So I think Josefa has just joined after the prayer. Josefa, from here, just remember one thing. In the numericals which you were asking, in forward bias, the diodes get replaced with a straight wire. And in reverse bias, it gets replaced with an open circuit. So in this circuit, this diode is connected in forward biased, and this is reversely connected. So just remove this diode from the circuit because no current will be flowing if it is an open circuit, and replace this diode by a single wire. Now you know how to solve questions from your current electricity. Like this only questions come. Fine. So identification, that's why I was emphasizing on learning of the identification, whether forward, reverse, which one. Note it down. PN junction is over. One very small topic for 5 minutes, that is rectifiers we have to see briefly. Note it down. Text me done. I'll start with rectifiers. Class, last topic, rectifiers. Rectifiers are very easy. Just remember, these just convert, these are divided AC into DC. The process of conversion of AC into DC, alternating current into direct current, is known as rectification. And the machine that does this function to convert AC into DC, that machine is known as rectifiers. Like in your mobile chargers, when you charge your mobile phone for a certain period, it gets charged. That this is also related to capacitors. One example I had told you when we were using regarding the flashlight of mobile phone, that was for capacitor. So mobile phone charger is for the rectifiers. Now just remember this fact that it converts AC into DC. Two types are available, half wave and full wave. Here you just have to remember their waveforms. Transformers we did know. So similar to transformers only. See in half wave. It's a step down transformer that has been connected. One diode is only present here. See, only one diode is present here. Let's say this is the input voltage. This is the input voltage that is given to you, input one. And this is the output voltage that is given. Now see what will happen. When this circuit will be developing positive charge. So positive with the higher potential with the P type, that will be forward biased. So it will detect, the circuit will immediately detect it. So this will lead to an output. Now when it will be negative, reversed bias, it won't detect it. So nothing. Then again it will be positive. Again it will detect it. Negative, it won't detect. So like this, you will be getting waveforms. Half wave will be there, half wave not. Since half wave you're obtaining, that's why we call it as half wave rectifiers. Now, just the opposite cases in case of full wave. No, this PN junctions are not there. I was saying two diodes will be there in case of not exactly opposite function. You will be having two diodes. So now what will happen? See. This is the input voltage, normal input voltage of AC you get. And direct current, you do not have sinusoidal curves, it is converting AC into DC. See, when forward here, it will be negative here. For D1, it will be positive and D2 negative. So positive with the P type, it will detect it. Then came negative. Now negative is not being detected by D1 because it becomes reversed bias. But see, when it is minus for D1, it is plus for D2. So it means now the gap that was being kept because of lacking of two conductor diodes, only because of single conductor that was present in half wave circuit. Now that deficiency is covered by D2. So D1 for the first one, D2 for the second. Now again, this will be plus, this will be minus. So plus one, it will detect. Again, it will be minus. This does not have to detect this. But here it will detect, D2 will do this. So these are detected by D1, these are by D2. So you get complete full wave without any interruption. That's why we call it as full wave, and the rectifiers are known as full wave rectifiers. Any doubts you have, class, let me know. Note down these 3 points. That completes your syllabus. Do not do any other part. Every rest of the parts have been erased from your syllabus. Semiconductors, in semiconductors, you just have till this point. Rectifiers also, you just have to do this much briefly only. Note it down, text me done once completed. Quickly write it down. So all those who have completed, you all can leave. No class will be on Thursday, so that you all can get a 1 week time gap for accumulation of all the doubts and whatever backlogs you have. So then next week we'll start with the revision classes. So this completes with your lesson. All right. So thank you so much, class. All those who have completed, you all can